Hi, and welcome once again to day 19 of Just Start Programming, the Rust programming language. The other day, our topic was all about closures, and it was tough for me to absorb those new concepts. So today, let's revisit it once again and do a quick review before we proceed with iterators. So join me once again, do it live in one take, no shortcuts and no secrets. Well then, let's just start programming. All right, so we're back. Let's review closures. Okay, so it's still part of chapter 13 of the Rust book under functional language features, iterators, and closures. Okay, so closures, anonymous functions that capture their environment. Let's go through the example. I think this part here, this is new to most of us. Yeah, so you have this uh, vertical bar or the pipe. So this represents the closure, and this one is called within this closure. Unwrap or else. Yeah, so here's the explanation. This is the closure expression. It's an argument to unwrap or else, and the body of the closure is this one. So we can think of it as a function, and inside the function, this is the implementation, the logic within that function. Yeah, but closures doesn't have fn. Here doesn't take any parameters. It doesn't have this one, open and close curly brackets. I think because it's only one line. And then there's this concept about closure type inference and annotation. Okay, from here, optional type annotations to the parameter and return types. So here we can explicitly say, okay, the parameter num is of type unsigned integer 32. And the return is also unsigned integer 32. So this one, this num. Threading is somewhere. Where was it? Oh, I think it's something advanced, multi-threaded. So we're still quite far. Although it's tempting to directly jump here, I would say let's stick to the program and just continue with the basic ones first before we jump into the advanced. And here's how it looks. So this one is a function. You have the parameter, the type, the return, and then the block where the function executes its logic. So for closure, it looks similar. So instead of parentheses, open and close, you have this vertical bar or the pipe. Yeah. So you can also place the open and close curly brackets. Example closure. So it takes in x as the parameter, and then returns x. Okay. This one will have an error, mainly because over here, what was the term? I think it was infer. Yeah, it was trying to infer that, oh, you used a string over here, then it means that the expected data type is a string. But then we used an integer, i32. By default, this is i32. Now, yeah, the compiler will say expected. Okay, so it was expecting string but found integer. Capturing reference or moving ownership. I think this is the complex part. I think there was an fn, non-fn. What's the other one? There are different types here. Fn traits. Yeah, Fn traits. So you have Fn once applies to closures that can be called once. So a closure that moves captured values out of its body will only implement Fn once and none of the other Fn traits. If it moves captured values out of its body, so it will implement Fn once. And it can only be called once, while fnmut applies to closures that don't move captured values out of their body, but that might mutate the captured values. So these closures can be called more than once. And then fn applies to closures that don't move captured values out of their body and that don't mutate captured values, as well as closures that capture nothing from their environment. These closures can be called more than once without mutating their environment, which is important in case such a calling a closure multiple times concurrently. Okay, so here where f is fn1 straight, option string, so it will get a string. But where is it? Unwrap or else? I think it's referring to the previous. Is it this one? Unwrap or else? No, not this one. Give away. Unwrap or else. Sit again. Unwrap or else method on option T that we use in listing 13-1. Okay, so 13-1. This is 13-1, yeah. Unwrap or else. We'll stop here. Option. Okay, notice that the unwrap or else function has the additional generic type parameter f. Generic type parameter f. type is a type of parameter named f, which is the closure we provide when calling unwrap or else. So it is the closure provided. So if you imagine unwrap or else, then we have a pipe here, and then the body of the closure. So it's referring to this. So here fn once. So it can be called only once. Okay. Yeah, so if it's either some or none for the option, so if it's none, then it will call f. It will call the closure. Okay. And here, sort by key r dot width. So what is r? Sort by key list. So the list is an array of rectangle. Then array will have sort by key. So which key are we referring to? Key, which is r dot width. So it's referring to the width. It will be sorting by width. Let's see. We can run from here. 3, 7, 10. So it's correct. Sort by width. So it's in ascending order. And this one will not compile. Why it will not compile? What's the difference? So we have r previously and r dot width, but here we have sort operations, and we're pushing value from here. Attempting to use an fn1's closure with sort by key. Okay, so it says here it will not compile. To try and count the number of times sort by key calls the closure when sorting lists. This code attempts to do this by counting by pushing value string from the closure's environment. Into the sort options. Okay, so this is the closure environment. From the closure into the sort operations, which is here. It's outside. Value is also outside. And then moves value out of the closure by transferring ownership of the value. Ownership of the value to the sort operations. Push. So sort operations that push is taking ownership, not unless value you reference. So if you put ampersand, let me see if we have that in the code. 29. I think here. Sort by key. Okay, so I think we did that the other day. So let me just comment this out and see once again. Till here. So this one will not compile. Let's find value. It's value. I think this one. Find sort operations. Back closure called. Okay, this one is, it should be this one, the rectangle. Okay, so here, cannot move out value, a captured variable in an fmat closure. Move occurs because value has type string, which does not implement copy. Okay, so there's a suggestion here. Quick fix. Let's see. I think you should put ampersand before the word value here. Okay, consider cloning the value if the performance cost is acceptable. Clone. Oh, clone works. How about instead of clone, I will put sand here. So that one works as well. Let's run this one. 3, 7, 10. Yeah. So no issues. Oops. Let's keep it like that. Don't complain. Okay. Next. Yep, I think this is the last of the example. So this one works as well. 13-9. Sort by key because it's only capturing a mutable reference. Okay, where's the mutable reference? Mutable num sort operations. Mutable list. Okay, mutable value and then mutable source operations. I think this one. Num sort operations. Okay. Then we have R and then num sort operations. How do we know it's a reference to num sort operations? What is the explanation? Counter and can therefore be called more than once. Num sort operations counter. Okay. So it's an I32. Mutable, it can be changed. Oh, so we can do something like this. Can be, we're not borrowing. Are we borrowing? Capturing a mutable reference to the num sort operations. The FN traits are important when defining or using functions or types that make use of closures. In the next section, we'll discuss iterators. Many iterator method takes closure arguments, so keep these closure details in mind as we continue. Okay, so let's move to the next topic. Processing a series of items with iterators. The iterator pattern allows you to perform some task on a sequence of items. In turn, an iterator is responsible for the logic of the iterating over each item and determining when the sequence has finished. When you use iterators, you don't have to re-implement that logic yourself. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator to use it up. Oh, okay. That's interesting. No effect until you call methods that consume the iterator to use it up. So does it mean that it's not running? It's running only when you uh, consume the iterator to use it up. For example, in code listing 13-10 creates an iterator over the items of vector 1, v1 by calling the iter method defined on vect, so it's integer. This code by itself doesn't do anything useful. Okay. The iterator is stored. Okay, let's create another project. We save this. Close this one. And here, cargo new iterators. Dot. Here. Okay, that's nothing. Because it's unused. Okay. The iterator v1 underscore iter variable. The iterator is stored. Okay, iterator is stored here. Once we've created an iterator, we can use it in a variety of ways. In listing 3-5, chapter 3, we iterated over an array using for loop to execute some code on each of its items. Okay, iterator, yeah, for val in iterator, got val. Under the hood, this implicitly created and then consumed an iterator, but we glossed over how exactly that works until now. Okay, so in example 13-11, we separate the creation of the iterator from the use of the iterator in the for loop. Yeah. When the for loop is called using the iterator in v1 iter, each element in the iterator is used in one iteration of the loop, which prints out each value. Each element in the iterator is used. Okay, so it prints out its value. And just copy it here. Of course, it will print 1, 2, 3. 2, 3. In languages that don't have iterators provided by their standard libraries, you would likely write this same functionality by starting a variable at index 0, using that variable to index into vector to get a value, and incrementing the variable value in a loop until it reaches the total number of items in the vector. Iterators handle all of that logic for you. Cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences. Not just data structures you can index into, like vectors. Let's examine how iterators do that. the iterator trait and the next method. All iterators implement a trait named iterator that is defined in the standard library. The definition of the trait looks like this. Okay, trait iterator. Type item. FNX. Mutable reference to self, so it can change. Option self item. Methods with default implementations. Notice that this definition uses some new syntax. Type item. Okay, yeah, this is new. Type item. And self item, which are defining an associated type with this trait. We'll talk about associated types in depth in chapter 20. For now, all you need to know is that this code says implementing the iterator trait requires that you also define an item type, and this item type is used in the return type of the next method. In other words, the item type will be the type returned from the iterator. Item type will be the type returned from the iterator. Okay. Item. An item type. Okay. The iterator trait only requires implementers to define one method to the next. Okay, here. In this case, yes, next. Which returns one item of the iterator at a time, wrapped in sum, and when iteration is over, returns none. Where's the sum and none? Yeah, there's option. So option returns sum and none. Okay, we can call the next method an iterators directly. Listing 13-12 demonstrates what values are returned from the repeated calls to next on the iterator created from the vector. Okay, so we have iterator, iter next, iter next, iter next, iter next. Sum. Ampersand 1, 2, 3. None. Why do we have one here? Okay. So this is returned by this. This is the one we use in the assert. Okay. Let's copy this one. Be iter. Okay, what's the issue? I think that was mutable. Should be mutable. So here we put mutable. Compiling, Assert. Okay, assert macro. Assert equal macro. Okay, so no issue. Okay. Calling next method, an iterator changes the internal state that the iterator uses to keep track where it is in sequence. Okay, so it changes the state. Okay, so maybe that's why we have a mat here. In other words, the code consumes or uses up the iterator. Each call to next eats up an item from the, okay, so it eats up an item from the iterator. We didn't need to make the itr mutable when we used a for loop. Yeah, so previously here, it's not mutable. Okay, but here it is mutable. Each call to the next eats up an item from the iterator. Okay. Okay, the reason is because the loop took ownership of VITER and made it mutable behind the scenes. Behind the scenes. Okay, once again, behind the scenes. Black box. So it means that we just need to remember this rule once again. Because the loop took ownership of V1 iterator and made it mutable behind the scenes. It's for the for loop. Okay, so it works in the for loop. Yeah, but it simplifies things. So it's simple, but it's a special case, it seems. Okay, so that's why VITR here, you don't need to make it mutable. But what if we explicitly make this mutable? What will happen? Let's try it out. What? Works. Does not need to be mutable by default. Okay, so at least there's an explanation here, but they should still work. Yeah. Okay, so now we know. Yeah, that can be mat, or we can remove it. Where were we? Okay, here. Okay. Okay, here, mutable behind the scenes. Okay, also note that the values we get from the calls to next are immutable references to the values in the vector. Okay, the values that we call to next are immutable references to the values in the vector. The itr method produces an iterator over immutable references. So if we have this, it produces an iterator over immutable references. Okay, the references will not change. If you want to create an iterator that takes ownership of V1, and returns own values, we can call what is this? Into iter instead of iter. It's another function. Similarly, if we want to iterate over mutable references, we can call itermat instead of iter. This one we can try it out. So so behind the scenes, this one is mat in a for loop. What's our iter? Okay, here can I explicitly use mat here? Itermat instead of want to iterate over mutable references. Itermat cannot mutate immutable. Oh, okay. We use itermat if this is mutable. Okay, then here can remove it also. Doesn't matter. Then what this means is we are iterating a mutable vector. No, mutable references. Yeah, over mutable references inside the vector. Okay, so we can do something like that. Yeah, so that we remove mat here. It's enough to change. And here, so we can remove it as well. Okay. Okay. Methods that consume the iterator. The iterator trait has a number of different methods with default implementations provided by standard library. You can find out about these methods by looking in the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you are required to implement the next method when implementing the iterator trait. Methods that call next are called consuming adapters. Because calling them uses up the iterator. Yeah, so next, see it mentioned. So next, iterator changes internal state also. In other words, this code consumes or uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the items by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item into a running total and returns the total when iteration is complete. Listing 13-13 has a test illustrating the use of the sum method. So sum method takes ownership of the iterator. And iterates through the items repeatedly by calling next. Okay. Calling next. Next. Thus consuming the iterator. As it iterates through, it adds each item into a running total and returns the total when iteration is complete. Okay, here, so we have this, so there's only one here, one line here. It will return total 6, 3, 4, 5, 6. Okay, we aren't allowed to use v iter after the call to sum because sum takes ownership of the iterator. We call it up. Okay, sum will take ownership of this. Then we have total. So v1 iter here cannot be used. Okay, let's copy this part. Let me comment out this part. So we are using v1 iterator, then sum. Yeah, so of course this one will work. But what I wanted to do is over here, we try debug of v1 iter. So this one will have an error. Yeah. Use of move value. Yeah. Because it says that the function sum takes ownership of the iterator. Okay. We aren't allowed to use, okay, yeah. We already proven that. Then here, method that produce other iterators, the iterator adapters, okay. Define an iterator trait that don't consume the iterator. Okay. So they don't consume the iterator. Instead, they produce different iterators by changing some aspect of the original iterator. So methods that produce other iterators. So methods that consume the iterator, sum is one of the example. Yeah. Okay, here, which method? Okay, here. Listing 13-4 shows an example of calling the iterator adapter method map, which takes a closure to call on each item as the items are iterated through. The map method returns a new iterator. Okay, so it returns a new iterator that produces the modified items. Okay, so the closure will return a new iterator. The closure here creates a new iterator in which each item from the vector will be incremented by 1. Okay, but there's a compile time error. Error or warning? Okay, there's a warning. Unused map that must be used. Unused map. Okay, it says here iterators are lazy and do nothing unless consumed. Oh, that's interesting. Because here it's not used. We know that the closure is incrementing it, but it's not being used. uh, doesn't do anything, the closure we specified never gets called. Okay, so it says the closure never gets called. Okay, the warning reminds us why iterator adapters are lazy, and we need to consume the iterator here. To fix this warning, consume the iterator, we'll use the collect method, which we used in chapter 12 with environment arguments. This method consumes the iterator and collects the resultant values into a collection data type. In listing 13-15, we collect the results of iterating over the iterator that's returned from the call map into a vector. Okay, so this is, what's the term? Iterator adapters. So they don't consume the iterator, instead they produce a different iterator. Okay. Calling the map method to create a new iterator and then calling the collect method to consume the new iterator, create a vector. Oh, okay, so it created a new vector here. Okay, this one, I think uh, this one is considering different types. What's it mentioned here? It did not say. Okay, let's try this one. What's wrong with this? So it will increment v2. So v2 and vect would be equal. Okay, so it did not panic. So it's equal. Collect. It was calling this and now v2. What will happen to v1? v1 was not used. Maybe let's comment this out. So what did it say once again? Collect. And then calling the collect method to consume the new iterator and create a vector. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior that the iterator trait provides. Okay, because map accepts closure, so we can do some form of okay, this one, it's incrementing it, maybe some form of transformation here. And then finally collect and create a new iterator. No, new iterator and create a vector. Collect method to consumes the new iterator and collect a vector. Okay. Using closures that capture their environment. Many iterator adapters take closures as arguments And commonly the closures we'll specify as arguments to the iterator adapters will be closures that capture their environment. For this example, we use the filter method. It takes a closure. Okay, filter. Okay, filter is an interesting method, I would say. Usually, we will be using filter as we loop through the items. The closure gets an item from the iterator and returns a boolean. If the closure returns true, the value will be included in the iteration produced by filter if it returns true. If the closure returns false, the value won't be included. In listing 13-16, we use filter with a closure that captures the shoe size variable from the environment to iterate over a collection of shoe struct instances. It will return only shoes that are the specified size. Okay, so let's see. Partial and debug. Struct shoe. Okay, then we have a function, shoes in size. Vector of shoe, and shoe size is unsigned integer 32. It will return a vector of shoes. Vector shoes. Shoes into iterator filter. Okay, so here it's the filter method. This filter method takes ownership. Did it say? No. Capture the environment. And this one, don't consume the iterator. Okay, so here's the closure. Filter S. And okay, so S will have size. And then equals, so it's being compared to shoe size. Which one is the shoe size? Okay, it's provided here as the parameter. So if it's true, then it's included. Then collect will return that value. So it's a new vector. Okay, so here's the test. Let's copy this one and run it. Derive. So let's comment this out. Shoe size. It's a warning. Test. Let's see, filter by size. This is one of the test case. Config test. Filters by size. Let shoes. So it's a vector of shoe. Size 10, string, sneaker, size 13, sandal, size 10, boot. Okay. Let in my size vector shoe in size, shoes in size. Where's the shoes in size? Shoes in size is here. Shoes. Okay. Shoes. So it's a vector, And then shoe size 10. Vector shoe size 10. And then shoes iterator. Okay, so it's called here, so it will execute this one if it's 10, so it will be added. Okay, so 10, it means that it will pick up this one because it's equal. And then the new vector, okay, this is the new vector, will only have size 10 sneaker style. Okay, assert equal in my size. Oh, there's another 10 here. Okay, I didn't see that. So it will include, yeah, it will include boot size 10. Okay, so let's run the test. Okay, it was a success. So what can we learn from here? So we have a closure of, this is actually ampersand shoe. Filter of the vector shoe. Okay. And then s dot size equal to equal, is it equal to shoe size here? It will return this one. I was thinking, okay, let's make it more verbose. Can we put something like this? Should be fine. We had that visualization aid earlier, that function closure, the same. Okay, so that if that is being returned, can we do some depth to look nice? Okay. Collect. Then here, what I will do is debug. It's a shoe s ampersand s. Yeah, so I will be borrowing it. Just filter by size. Okay. Yeah. Why was it shown here? Okay. Because it tries to execute the test. Shoe in size. In my size. Okay. So does it mean that if I comment this out, we will not see any debug? Because it was never used. Let's see. Ah, it's true. It's true. It was never called. Or am I missing something? Let's review. Shoes. Shoe in size. No. I commented it out. Let's Yeah, that will run because we did collect here. We did a collect. This one will return vec shoe. Vec shoe. So what if I will create another variant of this? Just comment this out. And then instead of returning vec, I don't want to return anything. And I will remove collect. Okay, but I'm calling shoe in size here. So it won't display this debug. Yeah, it did not display the debug. Okay, that's interesting. It's only when you do a collect. If I call collect here, collect. Yeah, but I don't want to return the value. Consider type annotations needed. Where can we put the type? Iterator shoe. Okay, cannot satisfy underscore required by a bound in collect. Consider specifying generic argument vec. Okay. So can change this to this. Oh, now there's an error here. Not allowed type signature. Shoot. Consider specifying a generic argument. Where's the argument? Ah, here. Generic argument. Okay, yeah, but anyway, I think that is clear. If we are not calling collect, the closure will not be executed. Here. So if we run the test, there, it's okay, but we didn't see this being executed. Okay, so how about we put this back? Okay, so the return vector is totally new. It's new. Let's try, I think from here we could display in my size. Okay, so it's a new vector, and for I'll use for loop here for size in my size. Oh, that one looks redundant. It looks redundant. Size in my size. So this one should be iter. But we wanted to not colon. But why did I put colon there? Yep. Then print size. Size is a vector shoe. Okay, not print. Let's use debug instead. Debug. So debug was added here in. Was it added somewhere? Yeah, here. Shoe. Shoe. So we should be able to see the output. Ten sneaker, 13 sandal, 10 boot. Sneaker, 10 boot. Here. 10 sneaker, 10 boot. Why only 10? If size equals to shoe size. Okay, because 10 is the one used here as a filter. So in my size now contains a new vector, which we can display here. Where was the other ones? Okay, because we have a debug here, that should only display 2 items. 10 sneaker, 10 boot. Okay, so that is clear. Improving our IO project. See what's in here. Removing a clone using an iterator. Okay, we can improve. Okay, the IO project in chapter 12. It means that we can improve the implementation. Make the code clearer and more concise. So let's look at how iterators can improve our implementation. Config build. What do we have here? String values, and created an instance of config. Yep. We have clone. In our case, 12-23. So this one looks the same, pretty much the same. Okay, it's a reproduction of the config build function from chapter 12. At the time we said not to worry about inefficient clone. Oh, because we have clone here. Because we would remove them in the future. Well, that time is now. We need clone here because we have a slice with string elements in the parameter args, but the build function doesn't own args. Okay, it doesn't own args because of the clone, because it was being cloned. To return ownership of a config instance, we had to clone the values from query and file path fields of config, so the config instance can own its value. Config instance. Okay, so here we return this config instance. We had to clone the values from query. We have to clone the values from query. Okay. So that the instance can own its values. Okay. With our new knowledge about iterators, we can change the build function to take ownership of an iterator and its argument instead of borrowing a slice. We'll use the iterator functionality instead of the code that checks the length of the slice and indexes into specific locations. This will clarify what the config build function is doing because the iterator will access the values. Once config build takes ownership of the iterator and stops using indexing operations that borrow, we can move the string values from the iterator into config rather than calling clone and make a new allocation. Using the returned iterator directly. Open your, okay, this project, which should look like this. We have collect, yeah, we have collect here. First, we will first change the start of the main function that we had in 12-24 to the code in 13-18. Okay, here, 13-18. We have config args and wrapper else error. Then we display this error print line std error problem parsing arguments. The env args function returns an iterator. Rather than collecting the iterator values into a vector and then passing a slice to config build, env args, it returns an iterator. Rather than collecting iterator values in a passing the slice to, now we're passing ownership of the iterator return from to config build directly. What's that difference? Config build. So args we are borrowing. Here build takes ownership. And then unwrap or else. Unwrap or else. What's the difference? This one, of course, will compile. This one will not compile. Let's change the config build to look like 13-19. This still won't compile because we need to update the function body. Let's try to open up our chat. Let's go back to iterator. No. What was the topic? Closures. Functional language. No, not functional. What was chapter 12? IO project. Sorry. IO project. IO project is mini grep. Here. July 20. Okay, so it says in main.rs. Do we need to change? Print line under or process exit. We did something like this. env args. Okay, let's put that here. So instead of args like this, column args. So it says this won't compile. Then config here we need iterator for args. So let's open up libs. So config. Okay, config is here. Pub fn build. Pub fn build. Mat args. To change it like this. That's it. Mat args impl iterator. Implementing iterator item equals string. What is this? Item is string. So it will not compile yet. Not equal, but equal, just equal. Instead of ampersand string, this usage of IMPL trait syntax we discuss in traits and parameter section of chapter 10 means that the args can be any type that implements iterator. Any type implements iterator trait and returns string. Okay, so that's the interpretation of this. Args can be any type that implements the iterator trait and returns string items. Args. Okay. Then there will be an error for len. It needs to be next. Args next. Because args is now an iterator. Okay, let's copy this. Maybe we can comment out this old implementation. Let's put in new one. There. Alright, this should be args. Not next. Okay. So this is the explanation. Oh, we're just calling next. Query match args next. Arg. It's none, didn't get a query string. So it uses match. You can also take advantage of iterators in the search function. In the search function, search iterator. Vector, what we saw, vector lines. Can write this code in a more concise way. Yeah, I think for me, I modified the line here because I wanted to display this one. Search. Yeah, okay. So originally it was what was it? Contains query. Yeah, contains query. Contains query. Yes, instead of line, I created a found. And here, oh, lines, then you do a filter in line. Line contains query. Then collect. So collect will return this one. Okay, maybe what we can do tomorrow, we can edit it together and do some analysis, because now this one looks simple here, query, but what happens after this? If we include, okay, query is here, this can be part of that can be part of what we are trying to filter. But then collect will return a vector of found. But here I have push to results. So collect will actually return a new vector. So it's a new vector. Does it mean that we don't need to push? Yeah, that would be interesting. Okay, but I will leave that for tomorrow so that we have something to code tomorrow. So we'll do some coding tomorrow, and then this one is also an interesting topic. All right, so let me end here, and hope to see you guys tomorrow. Thank you so much.